Today, we're going to take a journey all the way from a nearly invisible clue at a crime scene to a fully functional piece of code. It's an amazing story about how a single scientific paper can be transformed into a powerful simulation that really just brings forensic science to life. So let's dive in. First up, we'll get to grips with the core problem, what I like to call the ghost in the machine. Then we'll see how some clever researchers used light to reveal it. After that, things get really cool as we watch the paper become a program, see that simulator in action, and then wrap up by asking, why does any of this even matter? Every crime scene is haunted by these invisible traces left behind. They're the ghosts that can literally make or break a case. And in the world of forensics, probably the most important and most elusive of these ghosts is the latent fingerprint, that partial, often distorted impression that just might hold the key.
We've all seen it in the movies, right? An investigator lifts a perfect, crystal-clear fingerprint from a glass. Well, the reality is a lot messier. Real-world latent prints are faint, they're smudged, and they're usually hidden on some really complex surface. They are the ultimate forensic puzzle.
And this right here, this is what we're talking about. A latent print left completely by accident. It's partial, it's smudged, and it is just full of noise and interference from the surface itself. Trying to analyze this, it's incredibly difficult.
So let's just get our terms straight for a second. On one hand, you've got exemplar prints. These are the clean, high-quality prints you give when you get a passport or something, deliberately collected. But on the other hand, you have the latent prints, the accidental, messy, and incomplete ones left at a crime scene. And those are the ones that really matter to investigators.
For decades, the way you'd make these prints visible involves some pretty messy and risky stuff. Dusting with powders, fuming with chemicals. The problem is, these methods can actually destroy the very evidence you're trying to collect. One wrong move and that clue is gone forever. There just had to be a better way.
And that better way? It came from a research paper, of all places, published by the IEEE. The researchers came up with this really clever, non-destructive method that uses the basic physics of light to reveal what's hidden in plain sight.
What's so brilliant about this whole solution is just how simple it is. The researchers designed this portable device. You can see the schematic on the left and the finished thing on the right. It's basically a special light box that uses a regular smartphone as its camera. Super low cost, totally portable, and incredibly effective. So how in the world does it work? Well, it's all about reflection. On a shiny surface, light hits the clean parts and bounces away from the camera in a straight line. That's called specular reflection. But when light hits the oily residue of the fingerprint itself, it scatters everywhere. And some of that scattered light goes right into the camera lens. The result? The fingerprint ridges appear way brighter than the background. It's just a beautiful, simple optical trick.
But okay, this is where the story takes a really fascinating turn. Seeing the print is one thing, but what if you could not only replicate this process, but simulate the entire chain of events, from the moment a finger touches a surface to the final enhanced image, and do it all in code?
This quote from the project's own documentation really just gets to the heart of it. The goal wasn't just to prove the paper's findings were right, it was to make the science behind it inspectable, runnable, and reusable. That means anyone, you, me, another researcher, can now experiment with it, learn from it, and even build on top of it.
And this is the result. A synthetic executable companion. It's a bit of a fancy name for a really powerful idea. A digital tool that simulates the whole process, from how a fingerprint is formed to how it gets enhanced. Suddenly, that scientific paper isn't just a static document anymore. It's an interactive tool. Okay, enough talk. Let's actually see this thing at work. We're going to walk through the simulator's entire pipeline, step by step, to see exactly how it turns a noisy, useless trace into a clean, identifiable fingerprint. So here's our starting point, the simulated raw latent print. And as you can see, it is a noisy mess. The ridge structure is barely visible. It's just full of random interference. Right now, this is forensically worthless. Okay, step one is to simulate the effect of that optical device we just saw. The program models how those yellow LEDs would make the fingerprint ridges scatter light, creating that contrast against the dark background. It's better, for sure, but we're still dealing with a lot of noise.
Now we move into the first stage of pure digital enhancement, using a technique called CLAH. The best way to think about it is like a smart contrast tool. Instead of just cranking up the brightness on the whole image, it works on tiny little sections at a time, pulling out details without accidentally making all the background noise louder. It's kind of like having a tiny artist meticulously going over every square inch of the picture.
And here's what you get. After applying CLAG, you can see the ridges are noticeably sharper. The contrast is much clearer. We're definitely getting closer to a usable print.
But the real heavy lifting, that's done by a signal processing method called STFT. Honestly, this is where the magic happens. Imagine you're sliding a tiny magnifying glass across the image. In each little spot, the algorithm analyzes the pattern to figure out two things. Which direction are the ridges flowing, and how far apart are they? Based on that analysis, STFT creates this, an orientation map. Each one of those little colored blocks represents the main direction of the fingerprint ridges in that specific area. This map is basically the blueprint for the final step. It tells the filter exactly how to connect the broken ridges and reconstruct the natural flow of the print.
And here it is, the final, pretty breathtaking result. Using that orientation map as its guide, the STFT filter has scrubbed away the noise and reconnected the broken ridges. What started out as a complete smudge is now a clear, continuous, and forensically valuable fingerprint. The transformation is just, well, it's remarkable.
But hey, does it actually work? This chart proves it does. It's showing the match scores from two different automated fingerprint ID systems. The blue and orange bars, those are the scores for the raw prints. They're really low. The green and gray bars are the scores after our enhancement, and they are way higher. So the takeaway is this. The process doesn't just create a prettier picture. It creates a fingerprint that computer systems can actually identify.
This all brings us to our final and maybe the most important point. This whole project is about so much more than just fingerprints. It's about a new way of doing scientific research. One where we take these brilliant ideas locked away in academic papers and turn them into tangible, interactive tools that anyone can use, test, and verify.
And that leaves us with a really powerful question to think about. This project took a complex forensic process and made it into a runnable simulation that anyone can try. So, what's next? What other vital research in medicine, in material science, in climate studies is just sitting there waiting to be unlocked and brought to life as a piece of executable science? The possibilities are, well, they're truly endless.